In this section, you will learn about subspaces of Rn. So in general, subspaces can be of some much bigger idea in math. So this is a very small thing to just think about subspaces of Rn. A subspace of Rn is any set H in Rn that has three properties. So again, a subspace is really a set of vectors that have these properties. So it has the property that 0 is in your set. It has the property that for any two vectors in your set, if you add them together, you're still in your set. It also has the property that if you have a vector in your set and you multiply it by a scalar, then the vector multiplied by that scalar is also in your set. In this first exercise, you're given three vectors, and you want to describe geometrically what the subspace of R3 generated by V1 and V2 looks like. And then is the vector V in your subspace? And then we'll think about why V1 and V2 generate a subspace. First of all, notice that they are subspaces of R3 because the vectors have three components. So because the vectors live in R3, we're going to be talking about a subspace or a smaller set in R3. So if we think about V1 and V2, those are two vectors in R3. So the subspace generated by V1 and V2 is really the span of V1 and V2, or all linear combinations. So C1 V1 plus C2 V2. The reason it's really just the span is because of the properties. So because of this property B, it says if you add any two vectors, it has to be in there, and this one says any scalars. So if you combine those two, it's basically saying any linear combination is also in your space. So your subspace generated by V1 and V2 is the set of all linear combinations of C1, V1, C2, V2. If we are generated by two vectors in R3, geometrically, this will be either a line or a plane. Because my vectors V1 and V2 are linearly independent, they are not multiples of each other, that means this will be a plane in R3. To determine if W is in this space, another way to ask that is W a linear combination of V1 and V2? And we know how to do that. So we're going to augment, and we can row reduce. When we row reduce, you get this last row of 0 equals 9. That's no solution, which means W cannot be written as a linear combination, so W is not in the subspace. To think about the connection between subspace and the span, we've kind of already talked about it because of those second two properties where if you add them together it has to stay in the subspace, and then the scalar multiples really just means that every linear combination makes up the subspace. So that's really the connection between those two. In exercise 2, we want to explain why the vectors that trace the unit circle do not generate a subspace. First property, you can say, is 0, 0 in the space? In other words, is 0 squared plus 0 squared equal to 1? No. So at this point, we could just say it's not a subspace. I just want to also show why the other properties fail. Keep in mind that to not be a subspace, only one of the three has to fail. In this case, all three do. So I'm just going to show you how all three of them fail. For 2, I'm going to say consider the point 0, 1 and the point 1, 0. Notice both of those are in the space. But what about when we add the 2, we get 1, 1. I just want to point out that these two are in subspace, then that means this one needs to be also, but 1 squared plus 1 squared does not equal 1. So second property fails. Third property, let's consider the point 0, 1, which is in the subspace. But let's take a scalar 2. Let my scalar equal 2. Then 2 times 0, 1 is 0, 2, which is not in the subspace. I can't even call it a space. It's not in the space. So this one fails also. There are an infinite number of vectors in a subspace, but we want to have a shorter way of representing what this space looks like. So we use a basis. So in other words, what's the base elements for a subspace? And a basis just has to be a set of vectors that are independent and span that space. So I want to determine if each of these sets are a basis for R3. So keep in mind, a basis is not unique. So there are lots of different bases that we could have. Are the columns of A a basis for R3? So first of all, notice that the columns are in R3. So that's a nice thing to make sure first. And then we want to know, are those 3 vectors linearly independent and do they span R3? So they tell us that row reduces to the identity. Since it row reduces to the identity, that tells me all 3 of those original vectors are independent. So they are linearly independent, which is great. And then it also tells me that they span all of R3 because I have 3 vectors, 3 linearly independent vectors in R3. So this is a yes. So basically, to find a basis for R3, we can just row reduce those vectors. And if you get the identity, then it will be a basis. So let's look at this second set. Some of you may be able to see that the third column is a linear combination of the first 2. I did not see that right away, so I row reduced this. In my process of row reducing, I see that I have 2 rows that are multiples of each other. So that's going to be a row of all zeros on the bottom, which tells me I'm only going to have 2 pivots. So it's not going to reduce to the identity. So it will not span all of R3. So this is not a basis. In part C, I can tell immediately this is not a basis because I only have 2 vectors. And if I only have 2 vectors, I can't span all of R3. In part D, I can tell it's not a basis for R3 because my vectors are in R2. And then in E, this is not a basis because I have 4 vectors in R3, which tells me they are linearly dependent. And then F is not a basis for R3 because my vectors live in R4. You learned what it means to be a subspace and that every subspace has what we call a basis, that the span of that basis would represent the whole space. There are 2 special subspaces that you will need to make sure you can find the bases for. The first is the column space, and the column space of a matrix is just the set of all linear combinations of the columns. The notation they use is col A. I tend to write col A with parentheses, so just know that those 2 things are the same. Exercise 4 gives you a matrix A and a vector P, and the question is P in the column space of A? So what that's really asking is, can P be written as a linear combination of the columns, which you guys know how to do. So we're going to augment and row reduce. To answer the question, can P be written as linear combination, I see that this system has a solution, which means P can be written as a linear combination of the columns of A. So P is in the column space of A. The second part says, in this case, when we say the column space is a subspace of Rm, what is M? So because P, which is a 2x1 matrix, and it's in R2, that means it is a subspace of R2. Exercise 5 asks you to find the basis for the column space of A. So keep in mind that a basis is the minimum number of vectors needed to represent the whole space. This is going to be a subspace of R4. So notice the columns have 4 components. So your subspace is a subspace of R4. To find the basis for the column space, you first identify your pivots. And those columns, so these are columns 1, 2, and 4, you take those columns from your original matrix. So 1, 2, and 4, and those are the basis for your column space. And keep in mind the basis is a set of vectors, so it's a finite set of vectors. Even though the space itself is infinite, the basis is a finite set. If I want to say what is the column space, you'd say the column space of A is equal to the span of all of those. So this is an infinite set because you're taking all linear combinations of these 3 vectors. And because I have 3 vectors in my basis, this would be a 3-dimensional space in R4. Again, I can't visualize that, but it's a 3-dimensional space in R4, which means it's not all of R4. So just some things to note about the column space. So the column space of an M by N matrix with real entries is a subspace of Rm. So it's the first thing. So basically your number of rows tell you the length of your columns. The second one just says, if you look at the columns of A, then the column space is the span of all those columns. But if some of them are dependent on the others, you just take some of those out. When a system of linear equations is written in the form ax equals b, then the column space of A is a set of all b's for which the system has a solution. And this last one just says the pivot columns of a matrix form the basis, which is how we found the basis. So you find your pivots, look at the columns that correspond to that, and that gives you your basis. The other important subspace is called the null space. And again, I usually use parentheses. The null space of A is the set of all vectors that map to 0. Or in other words, the solution to ax equals 0. So exercise 6 gives you a matrix and a vector p, and we want to know, is p in the null space or not? So if it's in the null space, that means it maps to 0. So you can just multiply. And remember to multiply, you do the dot product with the row. So it's 2 times 6 minus 3 times negative 10 minus 4 times 11. And negative 8 times 6 plus 8 times negative 10 plus 6 times 11. On the top, that's 12 plus 30 minus 44. I know immediately that that is not equal to 0, so that is not equal to 0, 0. So this vector p is not in the null space. And then the second part, in this case, we say that the null space of A is a subspace of Rn. Rn, notice that, well, they asked if P was in the null space, and that has 3 components, so N is 3. And A is a 2 by 3 matrix, and it's always going to be your number of columns. Exercise 7 gives you A and a partially reduced A, and it asks you to find the null space, or the basis for the null space, and identify one non-zero vector that's in the null space. So we always know the zero vectors in the null space. It's just a matter of, are there any others? To find the basis for the null space, we're going to augment with zeros. When you row reduce, that last column doesn't change, so I know that I can just put this row reduced form in. To find the basis for the null space, it's very beneficial to have your matrix in reduced row echelon form, so all the values above the leading ones to be 0, so we're going to change those values. So here I have my reduced row echelon form. I'm going to write down the general solution. I can see that I have 2 free variables, and that is x3 and x5. x4 is 2x5. x2 is 3x3 plus 7x5. And x1 is negative 3x3. Rewriting that as some vector times x3 plus some vector times x5, the coefficients of x3 are negative 3, 3, 1, 0, 0, and 0, 7, 0, 2, 1. And those are the vectors for your basis. So to get a vector that is in the null space, you can take any linear combination of these two vectors. So I could just take one of those vectors. So for example, negative 3, 3, 1, 0, 0 is in my null space and it is non-zero. So just some facts about the null space. This first one is just saying the null space of any m by n matrix is going to be a subspace of Rn. So it's the number of columns. So notice that in this example, A is a 4 by 5 matrix. And notice these live in R5. To test whether a given vector is in the null space, you can just multiply your A times that vector. If you get 0, then it's in the null space. If you don't get 0, it's not in the null space. And to identify a non-zero vector in the null space, if one exists, you can find the basis and then pick any linear combination of those two.